So this one is the first topic of block 4, which is about the simple phenomena of magnetism. The block 4 is electricity and magnetism. So starting with the 4.1, the simple phenomena of the magnetism. So these are the learning objective of topic 4.1, which is about the magnetism. First, what is the origin of the magnetic field? Like why the material behave like a magnet. The origin of the magnetic field, the material will behave like a magnet, is whenever the charged particles are moving, the motion of the charged particle so motion of the charged particle produces a magnetic field. Whenever the charged particles are moving, vibrating, oscillating, they always produce a magnetic field. So as we know, for an atom, the nucleus of an atom consists of neutron and protons. Neutrons are the neutral, protons are the charged particles, and around the nucleus, electrons are there. So electrons are revolving around the nucleus, and inside the nucleus we have charged particles such as neutrons, and neutron is a neutral such as proton. Now as a result, what happened, because electrons are charged particle, protons are charged particle, and they are also moving. So as a result, these particles, the motion of these charged particles such as movement of electron and proton, what will happen? The atom will produce magnetic field. So due to these charged particles, the atom will produce a magnetic field, and what we called an atom, a region which produces a magnetic field, we call these atoms as domain. So domain is a term which we normally use for the atoms which are producing a magnetic field. So what is the origin of the magnetic field? What is the start of the magnetic field? Is the motion of the charged particles. As we know, an atom consists of neutron, proton, and electron. So these particles are not stationary. As these particles are not stationary, they are moving. And due to the motion or the movement of these particles, such as electron and proton, the atom will behave like a magnet, or atom will produce a magnetic field. And we call that atom as domain. So how we represent an atom, how we represent a domain in terms of magnetic field. So we use an arrow to represent a domain. But you have seen there are materials, some of the materials behave like a magnet and some of the material does not behave like a magnet. So what is the reason why some of the material behave like a magnet and some are not behaving like a magnet, even though all the material consists of atoms? But why some of the materials are behaving like a magnet? Because their domains, their atoms, their magnetic field is arranged or aligned. So when the domains or atoms are arranged, that material will be a magnetic material. But there are materials in which these domains or atoms are not aligned. Domains are there or atoms are there, but they're not arranged, aligned. So as a result, what will happen? This material will be a non-magnetic material. So the origin of the magnetic field is the atom. Every atom, whenever you have atom, this atom will be a domain, means it will be a magnet. But because what happens, some materials, these atoms are aligned or arranged, so that material is refers to a magnetic material. Whereas some of the material, the atoms are not arranged or aligned, so we call that as a non-magnetic material. Is it clear? The origin of the magnetic field, the start of the magnetic field. So when a material is behaving like a magnet, So what does it mean? It means its domains are aligned or arranged. So in terms of this alignment, what happened? Like if I say this is a material in which the domains are arranged or domains are aligned, so this whole material will behave like a magnet. But within this material, there are two regions where the magnetic field is much stronger as compared to other parts. So the region where the magnetic field is stronger, the end of the magnet, where the magnetic field is stronger, like example, this is one part and this is the other part. So end of the magnet where the magnetic field is stronger, what we call that as a pole. So this, for every magnet there are always two poles. There are always two places where the magnetic field is much stronger than any other part. So we call those end as pole. And for every magnet, if one of the pole, like because north and south are opposite of each other, as you can see, like when we draw the direction, we say north, south, east, west. So when we draw the poles, when we work out, so if one of the pole we say a north pole, then what is the opposite of a north pole? The opposite pole is refers to south pole. So this north and south pole is not according to specific direction here. It is according to the opposite. Like if one of the pole, whenever you have any magnet, you will find there are two regions within the magnet where the magnetic field is much stronger than any other part, and these parts are known as the poles. So for every magnet, there are always two poles or two ends. If one of the end is known as the north pole, then the other end is known as south pole. So whenever you have a magnet, we always say that one is the north pole and the other is the south pole. So pole means the region, the space, the part where the magnetic field is much stronger than any other. So whenever we represent any other part within the magnet, whenever we represent a magnet, we always write what we write north and south. What does it mean, north and south? It means there are two opposite poles, two opposite ends, and they have very strong magnetic field than any other part. Like in this region, the magnetic field is much stronger as compared to any other part within the magnet. Then what about the concept of magnetic field? The magnetic field is refers to a region, the space around the magnet where other magnetic objects can experience force. So the space, the region around the magnet where the other magnetic objects, where other magnetic material can experience the force, that space or that region is known as the magnetic field. Like example, if I place a piece of iron, iron is a magnetic material. So what will happen? This iron will be attracted. But if I place, so iron is a magnetic material, so iron is attracted. If I place another, like example, a steel object, steel is also a magnetic material, so it will be attracted. So the space around the magnet, the whole region, this whole region around the magnet where the other materials can experience the force, the magnetic material is specifically magnetic. Like example, if I place a wood here, even though it is closer to the magnet, but it won't be attracted because wood is not a magnetic material. So the region, the space where we place a magnetic material and it is attracted by the magnet, that whole space is known as the magnetic field. And how we represent a magnetic field? There is a way to represent a magnetic field. So we represent a magnetic field by lines. We call that as a magnetic field lines. And these lines, when we draw from north to south. So the lines which represent the space around the magnet where the force, other magnetic object can experience the force, that whole region is known as the magnetic field. And how we represent a magnetic field? By drawing the lines between the north and the south pole. So this is a region, the space around the magnet where the other magnetic materials, where the other magnetic object can experience the force. And the direction is always, this is our assumption, it is always out from north and it is into south, the direction. And these lines means the space which are the object is there within these spaces. Like example, if I place an object here, here, anywhere, these lines are representing a magnetic field lines. So example, I did not draw a magnetic field line after this. So it means if I place a magnetic object here, because it is not in a magnetic field, so it will not experience any force. So region, the space around the magnet where the other magnetic material can experience the force, we call that as magnetic field. So basic idea is that this is a representation of the magnetic field by lines. So whenever we have a material consists of atom. And if the atoms are aligned or atoms are arranged, means that material will behave like a magnet. And if these domains, the atoms are also known as domains. So if these domains, there will be region where the magnetic field is stronger than any other part. There will be two regions. We call them as a pole. So we call that as a north pole and south pole. And we draw the magnetic field line from north to south to represent the region where the magnetic objects can experience the force. So what are the properties of the magnet? Whenever we have magnet, like example, the magnets have two poles always. Whenever you have any kind of magnet, there are always two poles. Like example, this is a bar magnet. So one is the north pole, another one is the south pole. What is the meaning of the poles? Poles means the region where the magnetic field is much stronger than any other part. And magnet attract the magnetic material. And what are the magnetic material? Such as iron, cobalt, nickel and steel. If we place these material, because these are magnetic material, so they will be attracted towards the magnet. But what if I place a copper? Copper is a metal. Will be attracted towards the magnet? Yes or no? If I place a copper, it will experience any attraction towards the magnet? No. So it is not, the copper is a metal. Metal does not mean it should be, all metals are not magnetic. The only material which are magnetic is iron, cobalt, nickel and steel. So if I place a copper, when we have an object which is made up of copper, it is not attracted towards the magnet. Same way, if I place a piece of aluminium, an object made up of aluminium, is it attracted towards the magnet? Yes or no? So it won't be attracted because aluminium is not a magnetic material. So students get confused with this. They think that all metals are magnetic. That is wrong. That is a wrong concept. All metals are not magnetic. Only few materials are magnetic or few elements are magnetic, such as iron, cobalt, nickel and steel. Rest other are non-magnetic material. They are not experience, even though it's a metal or a non-metal, but it does not experience any attraction from the magnet. So if an object is made up of iron, cobalt, nickel, or steel, it will be attracted. Otherwise, it won't be attracted. So as you can see here, the second is a horseshoe magnet. So even in horseshoe magnet, there will be two poles, like one will be north pole, then the other will be south pole. So whenever the magnet is there, there are always a region, the end of the magnet where the magnetic field is stronger. We call them as poles. And like poles of the magnet, maybe you have experienced when you bring the two identical poles of the magnet, like if a north pole is bring closer to the north pole, so as a result, what they do, they repel each other. They try to push each other. You can practically do this, like take two magnets and just push one of the magnet towards the other, and their like poles should face each other. What you will find, that the magnet, if you are moving, the other magnet also start to move away, because the two like poles or identical poles of a magnet repel each other. And if we have unlike poles, like north and south are facing each other, what happen as a result, they will be attracted towards each other. So like poles of a magnet, identical poles of the magnet repel, whereas unlike poles of the magnet will attract. Then around the magnet, there is a region, there is a space around the magnet, which we call that as a pole or end of the magnet. And if one of the pole, one of the end is known as north, another one is south. And the space around, like whole region around the magnet, this whole region around the magnet where the other magnetic materials can experience the force, what we call this whole region is known as magnetic field. And how we represent a magnetic field? We represent a magnetic field by arrow, by lines, which we call, these lines are known as field lines. And how we represent the field lines? They're always out from north and into south. So you can see, when we start from north pole, we continue to south. Starting from north pole, south. The distance between the lines shows the strength of the field. If the lines are closer, it means stronger field. So when the lines are closer to each other, field is stronger. So as you can see here, so if you see this region, this whole space, you will find the lines are very close to each other. So if the lines are close to each other, it means this is a point where the magnetic field is stronger. So if I say point A, the magnetic field is stronger, and it is obvious because it is a pole. Around a pole, the magnetic field is much stronger. But as we move away from the magnet, the distance between the line is increasing. Like here, the lines are closer at point B, but when at point C, the lines, the distance between them, we represent that they have a greater distance between the two lines. What does it mean? It means that the strength of a magnetic field is weaker. Like if we are moving away from the magnet, the distance between the lines will increase. Here you can see this point, the field lines are closer, but when we move away, the distance between the two identical field lines has increased. It means the strength has decreased. So region around the magnet where the other magnetic material can experience force, we call that as a magnetic field, which is represented by magnetic field lines. Is it clear, the concept of the magnetic field and the poles? So if I say I have 2 points A and B, which point the magnetic field is stronger? At which point the magnetic field is stronger? So it is stronger at A. Why at 8 is stronger? Because you can see the distance between the field lines is small. But here at B, the distance between the field lines is greater. And it is, the concept is that as we move away from the magnet, the strength of a magnetic field is also decreasing. So if you are closer to the magnet, you will experience the same magnetic strength of a magnetic field as compared to when you are away. Now, plotting a magnetic field lines, practically how we can plot a magnetic field line. So for this purpose, we use a plot. For this case, we use a plotting compass. What is a plotting compass? Maybe you have used this for navigation to find the direction. We use this plotting compass. What is a plotting compass? A compass which is used to find the direction, that's known as a plotting compass. Actually the plotting compass needle itself, the needle, there's a needle inside in this sphere, and that needle is actually a magnet. So the needle of the plotting compass itself is a magnet, and one side is not, the needle, the one side of the needle is not pole of the magnet, and the other side is a south pole. Like example, uh, or red or blue, normally we use for blue, we use for south, north, and red we use for south. So example, this is a plotting compass, the compass which is used to find the direction used by navigators. So north and south. Now how we plot a magnetic field, how we can work out the magnetic field of a magnet. So first what we do, we place the magnet. So this is a magnet. Example, this is a north pole of the magnet and this one is a south pole of the magnet. The north pole example is represented by a blue region and the south pole is represented by a red or a pink shade. So we have north and the south. Now, how to plot a magnetic field? So what we do, we place a compass here next to the magnet. So when we place a plotting compass next to the magnet, we know according to the magnetic field, the like poles, if identical poles are there, they will repel. And if there are unlike poles or opposite poles are there, what they will do? They will attract. So like poles repel and unlike poles will attract each other. So when I place a plotting compass next to the magnet, what will happen? Because the like poles will repel, so north will repel north and south will attract the north pole. So how the compass needle will appear? It appeared that the south pole is attracted. So this will be the part of the south pole, and the north pole is repel, but this is a needle, so it will appear like this. This is one needle, one made up of one material, but one side is south, another side is north. So south pole will is attracted towards the north pole of a magnet, and this is how the compass needle will point. So when the compass needle point in this manner, what we do, we place a dot. We place a mark here or a dot. Is it clear till this first point? Like till this point. So what we did, we take a magnet and we bring a compass next to the magnet. The compass needle is also a magnet. The needle of the compass is also a magnet, and in which the like, as we place two magnet closer, unlike poles attract and like poles repel. So south pole of a compass attract the north pole of a permanent magnet, and they will face each other. Then we mark a point, like this is a point which we mark. Now what we do, we will move the compass until So this compass is moved until what we see, that the south pole or the needle of the compass again in line with the last point which we mark. So when it is in line with the last point which we mark as we move the compass, so what we do, we will mark another point. Then again we move the compass until the last point which we mark come in line with the needle of the compass. So when the last point which we mark come in line with the compass needle, we will mark another point. Then we will move the compass until the last point which we mark come in line with the needle of the compass, and when it will come in line with the needle of the compass, we'll mark another point. And then we further move until we reach the south pole. So when we reach the south pole, what will happen? Because now the north will attract, or the compass needle will be in line, so how it will appear? It will appear like this. So the needle of the compass changes the direction and we mark the point. So as a result, when we mark the point, how it appeared, like this was a magnet, then there will be points. We will have different points. And we join these points. As a result, when we join these points, what it will show, this is a field line and this is representing a magnetic field region. Like this is a region where the magnetic field is acting. So this is how we can work out the magnetic field of a permanent magnet by using a plotting compass. Is it clear, the concept how a plotting compass can be used to sketch the magnetic field? Same way we can repeat on other side. So plotting compass magnet is the needle of the plotting compass is actually a magnet. So the two magnets, when their unlike poles are facing each other, they will attract. So we'll mark first point. Then we move this compass to a new position until it will come in line with the last point which we mark. Then we mark another point. Then we move the compass until the last point is in line with the needle of the compass. We'll mark another point. And we continue this until we reach the other end and we join the points to represent a magnetic field lines. So a plotting compass is used to identify the magnetic field lines or magnetic field of a bar magnet or any kind of magnet we can. So for this you need a bar magnet, you need a plotting compass, a plain paper and a pencil. Why a plain paper? Because you will place. So first what we do, place the magnet at the center of a sheet of a paper. So like we'll take a paper here and then we place a magnet. So a magnet is placed on the sheet of the paper. Then place the compass near one of the pole. So we'll place a compass here near the one pole so that the needle of the compass will point in specific direction. So the position where it is pointing, that will mark, and we continue this until we reach the other end. As you can see, what we did, we place a plotting compass, and this needle of the plotting compass is also a magnet, and opposite poles attract each other. So basically this is a south pole and this one is a north pole. So where the needle is pointing, we'll have point 1, dot 1 and dot 2. And then we move the compass to different position. Like example, first we mark dot 1 and dot 2. Then we move the compass until the dot 2 is in line, so we'll mark dot 3. Then we move the compass to dot 4, and so on we repeat. So this will be the sketch of a magnetic field around the bar magnet. Is it clear the concept how we can sketch a magnetic field for a bar magnet? Then what is the concept of induced magnetism? Induced magnetism means when magnet attract the other magnetic material, when a permanent magnet attract the other magnetic material, it cause induced magnetism. Basically the term induce means like producing or forcing a magnetism. Example, say you have a permanent magnet which is having two poles, north and south. So one side is a north pole and the other side we have a south pole. So north pole is there and there is a south pole. What is the concept of induced magnetism? Example, you have a piece of iron. Say this is a piece of iron. Iron is a magnetic material. What is the meaning of magnetic material? It means its domain will be aligned in the external magnetic field. Now what happened originally, even for every material, the domains are not aligned. Originally, the domains of the iron are random. But what happened when we bring this iron, closer to this magnet or within the magnetic field, so as a result of the magnetic field, what happened? The domains will be aligned. And when the domains will be aligned, when the domains originally they are not aligned, and but when we bring in a magnetic field, they are aligned. So what we call that as a induced magnetism. Means iron magnetic field is induced or magnetic field is forced into iron or magnetic field is produced within the iron. And whenever induced magnetism occur, there are always opposite poles will be there. Like example, as this iron is facing the piece of iron, we bring closer to the magnet. So and magnetic materials are always attracted by the magnet, so always opposite pole will induce. If north pole is facing the material, so this will be south and this will be north. So always opposite pole will produce in the material, and we call this as induced magnetism. Same thing, if we bring a piece of iron, so originally the iron domains are not aligned, but when we bring inside a magnetic field, these domains will be aligned, these domains will be arranged. So when the domains arrange now due to the magnetic field, means this iron will also behave like a magnet. And whenever object behave like a magnet, there is always poles north and south. But what will be the poles induced here? So always opposite pole will induce. If south pole is facing, what pole will be here? North. And the other side will be south, so that it can be attracted towards the magnet. So the concept of induced magnetism is the material, a magnetic material, when they are placed in the magnetic field of a permanent magnet, they also behave like a magnet. And when they behave like a magnet, we call that as an induced magnetism. Is it clear, the concept of induced magnetism? So as you can see, this one, we have south and north. So when we bring these paper clips, so opposite pole will be induced. So this will be north, then south. The next paper clip will be north, south. Another paper clip, north and south. But if I connect a nail here, iron nail, so what will be the induced pole here? If I north is here, so which pole will be there? South. Then north. Then we place another. So which pole will be there? South, north. So this is known as induced magnetism, that the material which is a magnetic material, its domain aligned in the presence of the external magnetic field, and it will behave like a magnet and attract it towards the object. Is it clear, the concept of induced magnetism? That when object force the other object to be magnetized and attract that object, we call that as induced magnetism.